Okay, so I will give a mini course about this topic, which is not actually a topic on geometric group theory, because you will see it's mostly dynamics on groups, but there are some geometry on this stuff, and this is a very old subject on group theory that has been pursued by many people, but mostly from a combinatorial point of view. So what I want to do here is to change the point of view in order you could see that there is something that's really happening in this stuff, and actually there are many open questions in this regard. Okay, so let me start by the definition. Well, there are many definitions, but this is a very natural definition. So you have a group. In general, the groups that I will consider will be countable groups. Most of the cases will be finitely generated groups, but actually the definition applies to any group. So you have a group and you put an order on the group, as for instance for the group of the integers there is a natural order. So you try to see what happens in general. So you have a group and you have an order, and you can ask many things. So I will ask for this order to be a total order. And of course, you want more. You want some compatibility of this order with the group structure. So, for instance, I can define many notions. So, the order is left invariant if the inequality f is smaller than g implies h f is smaller than h g. Okay, this is. Okay, this is the natural definition. Of course, you can define this in the same way. What is a right invariant order? And you say that the order is bi-invariant if f is smaller than g implies both hf is smaller than hg and fh is smaller than gh. Okay. So these are very natural definitions, and I think the point here is try to justify why this is interesting. So I think that the best way to do this is by providing examples. Okay. Of course there is a trivial group. Okay, this is a trivial example. But I will consider infinite groups. So the trivial example, if you wish, in this stuff is the integers. Yes, there is. Actually, there are two orders on the integers. Okay, the natural order, so the canonical order, and the reverse order. And this order will be bi-invariant because the group is abelian. So, of course. Any other example? The rationals, the reals. Okay, so okay, let's concentrate on countable groups. C2. Okay, you can put a lexicographic order on this, but actually you can order C2 in many other interesting ways, and there will be a talk, I think today, about orders on abelian groups. This is interesting stuff. Of course, you can take C2, C3. You can take C2 any cardinality actually. Okay, and this is an interesting remark. So you have to, I think you have to assume the axiom of choice to order this. But anyway, okay. Any other example? So I will give you an exercise. By the end of this course, this will be, I hope, this will be evident. But if you present the thing this way, I think this is not evident. So if you take the free group in two generators, this is an orderable group. Okay? This is a left orderable group. And actually this is a bi-orderable group. Okay? But actually it's not that easy to give explicitly an order on the free group. But this is an orderable group. And of course, if you have something which is shared by the integers and F2, well,
So what's an example of one left order on
it's an exercise. On Z2, sorry, on Z2, you take the lexicographic order, okay? And you compare on the first entry, and if they are equal, then you pass to the second entry. And this is an order, a total order on C2, and this is bi-invariant. By the way, in general, I will consider orders on only one side, and I will consider the left invariance. It is equivalent to consider right invariant orders, because when you do the transformation that you pass from the element to the inverse, you transform left orders into right orders. So if you have a left order on the group, then you transform this into a right order by saying that in the new order, G is, sorry, if you have an order here, in the new order, G will be greater than H if and only if, this is in the new order, so this is a prime, if and only if the inverse of G is, say, smaller than the inverse of H. Okay? So you have a left order here, and via this transformation, you transform into a right order. But be careful, this is another exercise. If you take a left order, sorry, thank you. Well, you can do the same if you wish. That was your question? Yeah. It's the same. It's the same. It's like reversing the order on the integers. Once you have chosen one, you can choose the other. Okay? Okay, so the remark, maybe it's will become clear with this exercise. If you have a left order on the group, it is not true that F larger than G implies F inverse smaller than G inverse. This is not true. Okay? And the exercise is give an example. Okay? Okay? If you try to do things just using the definition, you just say, well, F is greater than G, then I will multiply on the left by F inverse, then you get F inverse F is larger than F inverse G, which is the same as saying that actually this is an if and only if. The identity is larger than F inverse G, but if you want to pass the G to the other side, you have to multiply on the right. Okay, so you can do that if you have a by order, but if you only have a left order, you are not allowed to do this. Okay, this is at the level just of the definition. Now try to give an example where this happens. Okay, so I hope this will become clear by the end of this talk. Okay. Okay, and there are many other examples of groups. Yes.
When you say left order, do you mean left invariant? No.
Left order will be for left invariant total order. Okay. Okay, so LO will be left invariant total order. And more examples. So I will not describe all these examples. I think you know all of them. Otherwise, you will hear about these groups during these 2 weeks. So if you take the pi 1 of a surface, actually this group is biorderable. Okay, you can think about this as an exercise. This group is bi-orderable. Okay? For bi-order, yes. For left order, no. Except for the pi 1 of the of the of the projective plane. Yeah, of course. Okay. Okay, so pi 1 surface plus I will put. Okay, this is okay. The mapping class group of a surface I will put oriented and with some boundary. Okay, this is also this is left orderable, and this was discovered. This was essentially proved by Nielsen, but actually it appears in the work of Thurston. Braid groups. This is really great. These are left orderable, and this was proved by. This is a fascinating story because this was proved by Patrick de Hornoy using method from set theory and logics, and Thurston came out with a geometric method to order these groups. Okay, and Thomson's groups. I hope someone will say a few words about these groups and many other groups that appear in the literature. So the point is that there are many groups that are left orderable, and this makes that this is an interesting notion to look at. Okay. Okay, let me give another exercise. Okay, now this is a remark. If G is a left orderable group, then it has no torsion. Okay? Why is that? Well, the proof is very simple. If you take an element which is different from the identity, I will use 1 for the identity. Maybe this is not a good notation. Maybe 1 is positive, so it's better to write identity. So if you have an element which is different from the identity, then either it is positive, which means larger than the identity, or negative, which means smaller than the identity. Then so this is negative with respect to this order, or it is larger than the identity. Okay? And now you start playing with the inequality. So if f is larger than the identity, then I am allowed to multiply by something on the left. I will multiply by f on the left. So what I get? F to the square is larger than f. Is it okay? I am just multiplying on the left. Okay? But f was already larger than the identity, so you get this. And then you multiply again by f on the left. And what you get is f to the 3 is larger than f to the square, larger than the f, which was already larger than the identity, and so on. So all powers of these elements, of this element, are positive. So the element cannot be of finite order. And of course, if f is negative, is smaller than the identity, you can do the same stuff. Okay? So if a group is left orderable, then it is torsion free. Okay? Here is another exercise. Give an example of a group which is torsion free but not left orderable. Okay. So being left orderable is stronger than being torsion free. Okay. It's not that easy. I mean, you have to think a little bit and maybe trying to modify a little bit the integers. You will get something, but it's not that easy. Okay. For instance, if you have an abelian group, being torsion free and being orderable are the same. Okay. So you have to go beyond abelian groups. Okay, and let me give another kind of exercise, just to show that if you just keep this approach using the definition and inequalities, you may get lost. So give an example of something. Give a group, a left order group. So now LO is for left order group, and F larger than the identity such that the conjugate of F is smaller than the identity for some element in the group. Okay. Actually, this is somehow saying that the left order is not invariant under multiplication on the right. The problem here is the multiplication on the right. Okay. Good. So now I want to go to the history of this stuff. So I think that if you trace back the history of this theory of orderable group, you have to go to Dedekind. I think it's like that. When he introduced the axiomatization of the real numbers using cuts. Was it Dedekind? Yes, the Dedekind cuts. Okay, okay. And you see the notion of order which is present in that view. And soon after that, Holder realized that some of the issues involved in Dedekind's proof were actually only group theoretical. So in the Dedekind's proof, there is naturally the structure of the rationals as a field, but actually there is something which is only group theoretical, and he has a very nice theorem that I think will be discussed tomorrow. He didn't prove it in full generality, but anyway, I will state it as the theorem of Holder, so some people complete the proof after that. So the theorem of Holder says the following. So let me remind, before stating the theorem, let me remind a fundamental property of the reals, which is the Archimedean property. So the Archimedean property means that I will state it for a left order group in general. This is, by definition, is that for every F which is larger than the identity, and for every G in the group, there exists some power such that well, this power is larger than G. Okay? This is a definition. This is the Archimedean property which holds for the reals, and you can define in more generality for left order groups. Okay? Okay, the theorem of Holder says the following. It's a characterization of groups that admit a left order which is Archimedean. Okay? So a group G admits an Archimedean order if and only if G embeds into the reals. I will denote the reals this way, okay, with the sum. This is the group structure, the sum, okay. And actually, this is not only an embedding, this is an order embedding. It means that if you have the Archimedean order on G, then the map that you will build will respect the order. So this is an order embedding. Okay? This is reminiscent of the proof of Dedekind, of the cuts in the real life. But there is only the notion of order here, and actually you assume at the very beginning only that the group is left ordered, and the conclusion is very strong. The conclusion is in particular that the starting group was abelian because it embeds into the reals. Okay? Moreover, the cardinality of G cannot be larger than the cardinality of R. Okay? If you see here, for instance, well, I erased the blackboard, but if you take C to any power, Aleph, okay? To any power, this is a left orderable group. But it cannot have an Archimedean order because of this theorem, just looking at the cardinality of this group. This is too big to be included in this, in the group of the reals. Okay? Well, this is an exercise, but it will be discussed by who's giving the talk about Holder's theorem. So tomorrow, yeah. No, today. Aye. Okay. So this is Holder's theorem. Very good. And well, actually, as I said, this was not completely proved by Holder because Holder, the theorem of Holder was for biorders which were Archimedean. And it was extended to left order by a guy whose name was Paul Conrad in the 50s. Okay, and well, he gave a proof of Holder's theorem for left orders, not only for biorders, but he introduced another notion of left orders, which is somehow an intermediate notion between biorderable and left orderable, and which is a very good notion and very useful notion. But he did it in a very algebraic way. So I will give the definition. So here is the definition. So a left order on a group G is Conrad or Conradian if well, I give the definition. It's hard to understand what's happening here. For every f which is positive, for every g which is positive, there exists some n such that f g to the power n is larger than g. Okay. This is a definition. And somehow he managed, using this definition, actually he came out with this definition in a natural way, trying to generalize the Holder theorem. Yes?
Is n necessarily positive or negative?
Wait. No. So what I would like to say is that if there is an n such that this holds, then this holds for an n which is positive. Okay? I will need to check that. Okay. Yeah, of course. Look. This is the kind of thing that I think I can do. So if you are able to prove, for instance, that f g to the power minus 2 is larger than g, then well, I will start summing inequalities here. Of course, g is positive. So g is larger than g to the power minus 2. Okay? So if you multiply by f on the left, fg is larger than fg minus 2. But fg minus 2 was larger than g. So you can realize the inequality with g with
So
exponent 1.
in this theorem, is it also possible that G admits a non-Archimedean order, and then, I mean, does it imply that all orders are Archimedean, and then?
No. You're right. For instance, if you take c to the square, this is a very good point. C to the square, the order that I gave in c to the square, the only order that I gave was the lexicographic order. But the lexicographic order is not Archimedean, because if you only look at the first coordinate, you will never be greater than the second coordinate. Somehow. It depends if you take the direct or the inverse lexicographic order. However, there is another way to order c to the square. It's just you see c to the square as, say, the group generated by 1 and pi, any irrational number here. Okay? This is c to the square embedded into the reals. Okay? And the reals are ordered, and you can push backwards the order to c to the square. And this is another way to order c to the square. Okay? And this, via this identification, what you get is an Archimedean order in c to the square. Okay? The lexicographic order is not Archimedean, but this order is Archimedean. Okay? Okay. Okay, here is an exercise. So most of these exercises for today are just manipulation of inequalities to see that something is happening here that, well, at the level of manipulation of inequalities, you don't really see what's really happening, but something deep is happening. So the exercise is that if you have this property, then you have the very same property for n equal to 2. Okay? If this happens, then for every f and for every g which are larger than the identity, one has fg to the square is larger than g. Okay? It's a good exercise. So what I have to say is that nobody noticed this fact until 10 years ago, from the 50s, and this is a very crucial remark. We will see why in maybe tomorrow, maybe today. Okay, but this is really crucial for some stuff. And this is an exercise. Just play with inequalities on the good side. You are not allowed to multiply on the right, but you will see something happens. Okay, so what is the content of the theory of Paul Conrad? Is that, well, he says having an Archimedean order is very restrictive. The group embeds into the reals, but sometimes you are interested only in constructing homomorphism into the reals, which are not necessarily faithful. Okay, and this notion captures this stuff. Okay, let me give a theorem. So I will come back to the proof of this. I think there is a talk tomorrow on Conrad's property by. Okay, and then I will come back to the proof of all of this. So the theorem says the following. So the theorem is by Paul Conrad. by Paul Conrad in one direction, and the converse was proved by Brodsky in the 80s, and it says the following. A group G is Conrad orderable which means that it admits a left order which satisfies this strange property here, if and only if G is locally indicable, which is a very bad name, but we cannot change it. Okay? So what is locally indicable? This means that actually here I am not assuming that the group is countable anything, so any cardinality. So locally indicable is a property which is focused on finitely generated groups. So G is locally indicable means that for every G naught which is a subgroup which is finitely generated, there exists a group homomorphism which is non-trivial into the reals. Okay? So the property of being locally indicable, which is something which has information about all finitely generated subgroups, can be transferred. Actually, it is equivalent to a property on orderability of the group. Okay? And I will give the proof of this during these talks. So there was a very nice application of this principle by, is it okay? Any question about the definition? No? Okay. So if you want to prove that something is locally indicable, you have to go into the world of orders and try to build. So the non-trivial, otherwise, okay, okay. So there is a non-trivial homomorphism. No, because this is why I put here orderable, not ordered. Okay. So there is a Conrad order in the group if only if the group is locally indicable. So in some sense, during the proof, you build homomorphisms that preserve the order. Okay? But this is the right way to state the theorem so that it becomes an if and only if. Otherwise, you have to start saying something about if you have a Conrad order, then you can produce a homomorphism, but the homomorphism is not necessarily faithful. So you have to look at the kernel and so on, and it becomes very complicated to state. This is the right way to state. Okay, so let me give an application of this idea. This is really a fantastic theorem, fantastic because of the proof as well, by Dave Morris Bit, which is the following. So I can use the word amenability. So if let G be an amenable group, and then G is left orderable if and only if G is locally indicable. Okay? So if the content of this theorem is that if you are able to order your group, then you are able to order in that way, which is Conradian, and because of this theorem of Conrad and Brodsky, you are able to produce many homomorphisms into the reals. Okay? So I will give the proof of this, I think, tomorrow. there is the notion of the convergent graphs. There is. Yeah, he gets more than Conrad. He gets a property which implies Conrad, but the important point is that he gets Conrad. Okay? And you will see tomorrow that this is a really fantastic proof. So let me just give an exercise. Well, this is not that trivial, huh? Maybe. Okay. Maybe yes. Okay. So give an example. Of a left orderable group which is not locally indicable. Okay? Okay, I will give any hint on this. I want to see what kind of example can you produce. So actually this was an open question for many years, okay? Until Thorson noticed that we were all stupid because there was an example which was in front of us all the time, okay? So, okay. Actually many groups are like that, many. Many groups arising from topology of three manifolds are like that, okay? Okay, I will come back to all these exercises during this week. Let me just say something. There is a really nice theorem which is a quite recent theorem from the last year by James Hyde and Yash Loda, thank you. There is another proof that I like very much by Michele and Michele, so Mattebon and Triestino, which answers a very a long-standing question on this stuff. There exists G, which is finitely generated left orderable and simple. Okay? In particular, it says that there are groups which are not locally indicable because there is no way to produce any homomorphism at all. Okay? This is really a fascinating stuff. It was open for many years. Okay. Okay, so these are the general definitions and some theorems that are, some of them are very recent, like this, and this is from, I don't remember, I think 2006. And now I will give another point of view of this stuff. And here is where dynamics enters into the play. So this is the dynamical approach. Okay, so and here is a general principle. So G, a group, is left orderable if and only if it acts. So on some space, okay. For me, omega will be endowed with an order. This is why I put an omega here, which is a totally ordered space. by order preserving maps. Order preserving, of course, order preserving bijections. Bijections. Okay? Is it okay, Pierre? Yes?
What do you mean by because any group can trigger
Faithfully. Thank you. Okay, that was your point?
No, no.
Okay. Okay.
So she don't need anything about omega?
Anything. This is very old. This is really, but this is still combinatorial. So the proof of this in one direction is somehow tautological. So this is the, okay, in this direction, this is Cayley, if you wish. So Cayley says that every group is a group of permutations. So that is the theorem of Cayley. I think so. Yeah. So you take the group and you make it act on itself by left translations. So this is theorem of Cayley. Now, if your group is left order, then you can consider that omega is your group, and the order on omega is the order on the group. And then you implement the Cayley proof, and what you get is that gamma, the group G, acts on itself by translations. And this is a faithful action, and it preserves the order because the order is left invariant. Okay? This is tautological. Okay? Is it okay? So the other way around is maybe it requires the axiom of choice, but we don't care about this kind of thing. So let me give the idea whenever gamma is countable. So if you wish, then we. So okay, the idea is the same if it is uncountable. So gamma will be gamma 1, gamma 2, gamma 3. You put a well order on this. Okay. Any cardinality for omega. And you will define the order on the group. You will say that F is larger than G if, well, F of omega 1 is larger than G of omega 1 with respect to the order on omega. Is it okay? Okay. Okay. Of course, they might be equal. So, in case of equality, you go to the image of the second point of the space. Okay. And if they are both equal, then you go to the third point and so on. Okay? At some moment, if F and G are different, they will act in a different way. Okay? So they will move some omega one to the left of the other. And then you will be able to compare these elements, and this gives you an order on the group, which is a total order. Okay? Is it okay? And the order that you are producing this way is invariant under left multiplication. Okay? Why is that? Because if you have this inequality here and you multiply on the left by h, since the group acts on omega preserving the order, you will have the same inequality. Okay? So this order is invariant under left multiplication. Okay? And actually, this might seem stupid, but actually this is quite useful because many groups are ordered that way. You somehow you build the space omega, where you see that naturally there is an action of the of the group G, and then for free you conclude that the group is orderable. Okay. And here is a theorem that nobody knows who proved it for the first time. So this is a folklore theorem, which says the following. This is a very important remark. So here I have a general statement with no cardinality assumption on the group. Okay. But if your group is countable, then you can embed gamma into the group of order preserving maps of the real line. But actually you can do better. You can embed your group in the group of homeomorphism of the real line. Okay? And which is quite useful because here you get continuity. Okay? That way you get order preserving maps, and you have to start working in somehow in a combinatorial way. But here you get continuity, and this is quite useful to study certain groups. Okay, so if G is countable, then G embeds into the group of homeomorphism of the real line. Yes?
So I had a question about the dynamical approach over
Yeah.
there. Your
Omega.
omega. Okay. So your omega is just some totally ordered space, right?
Yes.
Are these W1, these WIs are, is W1 like special in any way? Is it like a least element?
That's a very good point. Okay, so you just list the elements wherever you like. If you list the elements in a different way, then you will get another order. Okay, and this is very important. This is one way to construct. Whenever you have a group with an order, doing that trick, you can construct actually many orders on the group. Okay, so in general, when you have a group with an order, except for the cases like Z and some other cases, when you get an order on a group, actually you get many orders on the group. Okay, many orders. And this is one way to produce them. Okay, so here what I am saying is that for this case, you can take omega as being the real line, and actually not only the action will be not only order preserving, but an action by homeomorphisms. Of course, the converse is always true, so the converse is true even for G, which is not uncountable. So I will state it. So if G embeds into the group of homeomorphism with no assumption on cardinality, then G is left orderable. Okay? It's okay? So now I can give you the solution of one of the exercises. Okay? Half of one of the exercises. So remember, the free group, I claim that the free group is an orderable group. Actually, using this stuff, you can very easy. So it's very easy to see that it is left order. By order, it is more complicated. So why is that? Because if you take, in order to prove that the free group is left orderable, you only need to realize this group as a group of homeomorphism of the real line. Okay? Now take any two homeomorphisms of the real line at random. Using some bare category argument, in general, they will generate a free group. There is no reason to expect that some relation will appear. So if you take any two homeomorphisms at random of the real line, they will generate a free group. And using this stuff here, you get an order on the free group. Okay? It's very difficult to put the hands on the order. You only know there is an order. Okay? So, okay. Now, there is a question. assume that the order is bi-invariant. Okay? Sorry?
We were wondering how hard it might be to put your hands on two homeomorphisms.
On the real line.
Yeah.
Explicitly.
Yeah.
Ah, yeah, that's a good point. Okay, okay. So this is another exercise. Now this is actually a theorem. It's a hard theorem actually, but maybe you may arise with a proof. If you take these two maps, x into x plus 1 and x to the cube, then these two maps generate a free group. Okay? This is a theorem by, I don't remember who. I don't remember. I think that I don't remember. You can find this in the literature, and the proof is not easy at all. Okay? This is using Galois theory, and okay, it's not that easy. Okay, so this is an explicit group of free group of homomorphism of the real line. Yeah, I think it works for any p, a prime number here. I am not sure it works with any prime number, which is of course odd prime number, of course. Okay, let me explain something before this. So so I will give the idea of the proof of this. This is a constructed idea. This is very concrete, but there are some details to check in order to see that actually what you produce at the end are homeomorphisms and not only bijections of the real line. So the proof is like this. So you list the elements of the group. So the group will be say G1, G2, G3. You do any listing of the elements, okay, in any way. And now you go to the real line, and well, for the first point G1, you associate a point. So this is P of G1. Okay? Now there is G2. So G2 is either larger than G1 or smaller than G1. If it is larger, then you do the same, the following thing. So you say that PG2 will be P of G1 plus 1. Okay? So you can start at 0 if you wish. Doesn't matter. If G2 is smaller than G1, then you put on the left. Okay? Now there is G3, and there are three possibilities. It is on the left of G1 and G2, it is on the right, or it is in the middle. Okay? If it is on the left, then you subtract 1 from this. If it is on the right, you add 1 to this, and if it is between these two elements, you choose for G3 the middle point of this interval. It's okay? So this will be the configuration in case G1 is smaller than G3, is smaller than G2. Okay? So assume that this is smaller than G4, then P of G4 will be here. If now the G5 that comes in the list is between G2 and G4, PG5 will be here. Is it okay? It's just.
So when you write
No. This is any listing of the group elements. Any listing. Yeah. Okay? If you think a little bit, these points have to go to infinite in both directions. Okay? Because there is no torsion. So G1 to the square is larger than G1, so there must be some point, some element going to the right, to the right, to the right, and similarly to the left. Okay? And now the group G has a natural action not on the real line, but on this set of points. So if you have an element G in the group G, then it will move P of Gi into P of G Gi. This is the Cayley action. Okay, just move to the under the action of G. Is it okay? So G acts on P of G. Okay. Now the exercise. This extends continuously. Okay? This is an exercise. I mean, it's very important to choose the midpoint at each step. If you choose another point, and you may have problems of continuity at the end. Okay, but if you are choosing the endpoint, the midpoints, wherever there is some intermediate elements, then what you get at the end are continuous maps. Okay. Okay, this might seem trivial, but so question 1. Assume that the order is bi-invariant. Okay. So you do this procedure. You have an order on the group, then you can construct this map P, and then you have a realization of the group as a group homeomorphism of the real line. Okay? But if your order is bi-invariant, you should obtain something which is nice. So the question is, what kind of action you get? Okay. And the same question if the order is contrarian, what kind of action you get? Okay, you will get some particular actions. Okay. And this is somehow the spirit of the dynamical approach. You would like to translate algebraic properties related to the group and the order into dynamical properties of the action which is associated to that order, to the action on the real line. Okay? And then you want to do some dynamics and using ideas from foliations and topology to discover some features. Okay. Okay, now I will, so how much time do I have? Pierre?
14 minutes.
Okay. This is another notion that will be very important in these talks, the space of orders. This is another way to put some dynamics on this stuff. And this is a very nice object which was introduced. So I was told by of this by Gis. The reference is by Adam Sikora, and I should put the name Chaboti here in order to avoid problems, because it is really an idea that goes back to Chaboti. So as I said before, when you have a group with an order, by doing this trick of changing the points, you can build many orders. And you want to understand the group. Okay? So I will consider all the orders that I can put in my group. Okay? So what is the space of orders? So you can LO of G will be the set of orders of the group. So the set of all left orders, I will write it completely on G. Okay, this is just a set. And this is something that depends only on the group. Okay? And of course, you can define the space of bi-orders and there is another space that I will denote. CO is the set of all Conrad orders. Okay? So these are sets. Maybe this is empty. Maybe the group is not bi-orderable. Maybe the group is left orderable but not Conrad orderable. This happens, for instance, if the group is simple. If the group is simple and finitely generated, there is no homomorphism into the reals. Therefore, there is no Conrad order, and so this space is empty. Okay? Anyway. But the natural thing to do is to put some topology, some structure in this space. Okay? And there is a natural topology in the space of orders, which is the Chaboti topology. Okay? What is the Chaboti topology? Okay, I will give the definition. Even I am not doing any hypothesis on the cardinality of G. So I will define the topology in the classical way by giving the basic elements for the topology. It's okay? So what is the topology? So the neighborhood of an order. This is an order on G. Say a left order on G. Which means this is a point in the space of left orders. And I want to define the neighborhood of these points. So a set of orders that are close to this order. Okay? And to define the notion of closeness, what I will need is a family, a finite families of inequalities that are satisfied by this order. Okay? So assume that F1 is larger than G1 and F2 is larger than G2, etc. Fn is larger than Gn. Okay? Then the neighborhood of this order associated to these elements F1, Fn. So I will put here F1, G1, so on, Fn, Gn. Okay, this neighborhood will be the set of all orders prime for which these inequalities are still satisfied. Okay, so that for which F1 is still larger than G1, F2 is still larger than G2, and so on. Is it clear? Okay. And this is the typical construction a la Chaboti, because you are only taking finitely many conditions on the definition. So of course, if you want to define a neighborhood which is close, which is smaller around this order, you will need to impose more conditions on the inequality. So more inequalities. Okay? Okay, exercise. The space of left orders of the group with this topology is what? Is totally disconnected. Okay, if you have two different orders, then they are different because they do something different. In there are some f and g for which f is larger than g for one order and is smaller than g for the other orders, and this produces immediately a neighborhood of one of the orders that doesn't contain the other. Okay, so this is totally disconnected. So this is the part of the exercise. It is always compact.
So, I maybe I don't understand well that neighborhood. If you think the order as a function from the set of pairs to the set 0, 1, then this is just compact open topology.
Compact open. Yeah, I prefer to use -1, 1. Okay, okay. For me, 0 because they are equal. Okay, -1, 1. I think yeah. So, but be careful because I understand your idea. Actually, this is the idea to prove compactness. Okay, you have to do some identification between orders and maps from the group into this space of 2 points, but these maps have to satisfy certain properties that come from the group structure. So, for instance, the order is transitive. So, if the function on a pair is 1 and the other pair is 1, then the action in the transit pair is equal to 1. So, you do some argument like yours in the space, not of all the action, all maps, but in the space of maps that satisfy these properties. Okay. So use compact open topology? No, use Tikhonov theorem. To prove that this space is always compact, independently of the cardinality of G. This is because of the way we are defining the topology. Actually, if G is finitely generated, say generated by G1 up to Gn, and you can give a nice view of this topology. Actually, you can put a metric on this topological space, which is quite natural. So if you have a group, then you can look at the ball of radius. So let me put here k of radius n with respect to this system of generators. So what is this? This is the set of elements that may be written as products of no more than m generators. Okay, this is the ball of radius n with respect to this system of generators. Okay, the set of elements that may be written that way. Okay, and if your group is left orderable, then you can define a distance between two orders, and you can say that well, the distance will be 1 over n if n, okay, sorry. Okay, I will write this here. So the distance between two different orders will be 1 over n if n is the smallest radius such that the orders do not coincide on the ball. Okay? So there are two elements in the ball such that for one order one is larger than the other one, and for the other order the reverse inequality holds. Okay? And you look for the minimum value of n for which this happens. Okay? And this is a metric. It's an exercise. It satisfies the triangle inequality. Actually, it is an ultrametric, and this implies the fact that the space is totally disconnected, and actually compactness appears for free. So just to finish, so I will come back to all of this. So this was just kind of an introductory talk. But I want to finish by giving the idea of Dave-Morris-Witt theorem. And we will close that proof maybe tomorrow or some day. So remember the theorem of Dave-Witt. So the difficult part of the theorem of Dave-Morris or Dave-Witt, I don't know, theorem is that if G is left orderable and amenable, then G is locally indicable. Okay? So you can produce, if having an order on the group allows to produce many homomorphisms into the reals, provided the group is amenable. Okay? Otherwise, you may be in the case of simple orderable groups where there is no homomorphism at all. Okay? But remember that, I will explain this property is actually equivalent to be Conrad orderable. Okay? So the proof of Dave-Witt goes this way. He proves that if G is amenable and left orderable, he will produce a Conrad order on the group. An order with this inequality, with this set of inequalities, which is very strange. Okay? And now is the idea. So when you have the space of orders, you have more than the space of orders. You have the space of orders, and you have an action on the group on the space of orders. Okay? So G acts on the space of orders. Sorry. Okay? And the action is by conjugacy. Okay? So if you have an order, and if you have a group element, then you have a new order that I will denote this way, which is the image of this order by this element. And this order is defined this way. So F1 is smaller than F2 with respect to the new order if and only if the conjugate of F1 is smaller than the conjugate of F2 with respect to the original order. Okay? And this is an action. So you have your group, you have a lot of orders on this group, and you can move from one order to another one by conjugation. Okay? Very good. And this space is compact, and this space is metrizable if the group is finitely generated. So let me assume here that the group is finitely generated. Why is that? Because we want to prove a property which is only local, that it only involves finitely generated subgroups. So I will consider that G is finitely generated. Okay? So G amenable, say finitely generated, left orderable. Then you look at the action of G on the space of left orders, and this is a compact metric space which is totally disconnected, and you have an amenable group. And because of one of the equivalents of amenability, there exists a mu, which is a probability measure on the space of left orders, which is invariant under the action. Okay? Okay? Something you cannot put your hands on that. You know the group has an order. It has a set of orders, which is a topological space, which is compact. If the group is amenable, there is an action and there is an invariant probability measure. And the key lemma, and here I will stop, key lemma, and this is really fantastic. This is an application of Poincaré recurrence theorem, is that you only know that there is an invariant probability measure. You don't know what is this measure, what is the space of orders, but there is a very simple lemma that shows that mu of Conrad's orders equals to 1. Okay? So there must be some Conrad order. And this is the end of the proof. So it's okay? So I will give the proof of this. You will see this is just playing with inequalities and so on. This is Poincaré recurrence theorem. Okay? But as I said at the very beginning, this is introductory, but somehow this gives you the idea that if you put dynamical methods in this stuff, which is a priori is just combinatorial, you get many information that otherwise it's very hard to realize. Okay, I will stop here. Thank you.